This is the Physical Activity Researcher Podcast, a podcast for researchers of sedentary behavior, physical activity, and sports. Join for a relaxed dialogue about research design, practicalities, and, well, anything related to research. Learn from your fellow researchers useful and relevant information that does not fit into formal content and limited space of scientific publications. And here is your host, researcher and entrepreneur, Olli Tikkanen.
Welcome everyone. I'm very excited about today's episode as we are going to talk about accelerometry and activity tracking. Our guest, expert in the theme, is working as an assistant professor of integrative physiology and health science at Alma College in Michigan, US. He studies the accuracy and reliability of various physical activity monitors and also uses them as intervention tools to help individuals become more physically active. Ladies and gentlemen, I'm honored to introduce our guest, Assistant Professor Alexander Montoye. Welcome, Alex.
Thank you, Ali. It's great to be on the podcast.
So, what kind of things you are working at the moment?
Sure. Well, as I'm sure everybody is affected by COVID, our data collection here is pretty limited at the moment. So what we're really doing, and what's actually been a really nice silver lining to all this, is oftentimes we find that we collect much more data than we have time to fully analyze. You know, we'll be working on projects and we'll be able to address our main outcomes and work on those related papers. But then we have these very rich data sets with all kinds of secondary outcomes that we can sometimes look at, and that's always in the back of our minds. But you lose time among everything else that's going on. And so with data collection being so limited right now, we've had a chance to go back, revisit some of the data that we have and some of the study questions that we asked, and able to start addressing some of those secondary outcomes. And so mostly data analysis and writing right now, which are two of my favorite things. And so it's been a productive summer. It's been really nice to feel like I'm getting caught up and that we're doing full justice to the projects that we have completed over the past few years. So yeah, work on items from a number of areas. We have a number of accelerometer data sets that we are trying to derive meaningful outcomes from. So I'm sure we'll talk about it as the podcast goes, but looking at things outside your just traditional measures, we've done a lot with looking at activity intensity. So, you know, light, moderate, vigorous, and even sedentary behavior with accelerometers, but also trying to start looking into sport specific movements, things like, can we detect jumping? Can we detect side movements, what we call shuffling or cutting type movements from an accelerometer? And what does that mean in terms of understanding what happens in a sport context in order to be able to quantify training load? And even when people get injured, can we look at those data and compare them to people who aren't injured to understand how close injured individuals are to being back to full capacity or being ready for return to sport? So a number of areas related to accelerometer analysis currently going on.
Yeah, that's a good point, that you actually now have time to look at the data. I think it's the same with everyone, that you collect more data when you get funding and you don't really have time to look into it. So have you found something interesting in your secondary outcomes when you have had more time to actually analyze the data?
Yeah, it's a good question. You know, in a lot of my roles on these types of projects, I'll work on the data analytics end. And so I'm not necessarily as familiar with the research the population, let's say, sometimes. So for example, I'll do a lot of analytic work in working with pregnant individuals or working with athletes without necessarily fully understanding or needing to understand why that population is the population that this research group is interested in working with, or what the unique challenges are with those populations. And so for this summer, it's been a really big learning curve for me, because I've actually picked up and led writing on a lot of these projects that I may not normally have been involved with, just because I happen to have more time than some of the others with our research groups. And so that's been fun. I haven't gotten pushed out of my comfort zone that far in a long time, but really getting a better feel for what the physiology is in some of these specific populations, but then also getting back to and reading more on the theoretical end for some of these high level modeling techniques that we use to try to translate our accelerometer data into meaningful outcomes. The theoretical side would say you have all these different modeling types available. What's the theoretical framework for these models, and which ones should apply into a specific setting given the types of outcomes you're looking at or the type of population, right? So for example, some models are better suited for recognizing categorical variables such as activity type. Are they running or not? Are they doing lifestyle activities or not? Are they sedentary or not? And some are better for continuous outcomes, things like energy expenditure. Some also have a time sequence component, so it'll consider what somebody was doing in the previous interval and use that as an input to predict the next interval. So data that have a really strong time dependency can sometimes be predicted better with certain modeling types. So that's all the kind of theoretical basis on how you choose a model. A lot of times in practice, though, because models are fairly easy to implement and test, we'll just test a bunch of them, not necessarily the most scientifically sound method, but it allows us to look at a lot of data and see which ones actually seem like they have the best accuracy or the best utility. And so going back this summer and being able to really think about what the theoretical basis is and try to use that to advance some of the questions that we found we were struggling with in terms of modeling. We've had some limited success that way as well. So that's been encouraging to be able to get back to the theory on some of these models and use that to try to move forward where we've struggled.
Yeah, sounds interesting. And you mentioned earlier that you've been looking at the sideways movement, and I think that's a good point. Usually we kind of waste the information when we make a resultant vector out of the 3-axis acceleration. So what kind of applications you see for the sideways acceleration signal?
Yeah, good question. The motivation for this project came out with a couple of athletic training faculty that I've done some collaborative work with, who they work, at least the specialty of these two individuals is in knee injury, specifically ACL reconstruction and surgery, and what the outcomes are in terms of return to sport afterward. And so with ACL injury, it's almost always a one-sided injury. Some people will injure both ACLs over time, but when you have an ACL injury, it affects one knee. You go through a rehabilitation process. Typically, people are less stable in side-to-side movements than they are front to back or jumping type movements with an ACL. And so the faculty we were working with were very interested in understanding how much is the affected leg influenced, not only in terms of power production or jump height, but even as we start to move these individuals back into sport, whether that's practice or play, does it fundamentally change the way they move within their sport? Are they nervous about re-injuring their legs? So maybe they favor it and they perform certain movements where they rely more on the other leg. Specifically for the left and right movements, are they less likely to push off? So if I injure my right knee, for example, am I less likely to cut to the left because I would have to push with my right leg to accomplish that, right? So is there some asymmetry in terms of how often they would move left, do a quick leftward movement versus a quick rightward movement? Was kind of how the motivation came about for looking at that left-right component.
And do you do this from the waist or hip worn device? Is one accelerometer enough for studying this, or do you need in both legs?
It's a good question. What we've done so far is we've used a waist accelerometer. I know there's at least one other research group looking at similar questions, and they've used one mounted on the either the chest or the lower back. So it's certainly it's center of mass or close to that, or worn on the torso. We have not looked at ankle or wrist accelerometers. I would anticipate those would be considerably harder to detect things like a left-right movement. Really what you'd want to know is where the center of mass or where the torso is to give you an indication of the body's movement. But yeah, so far we've only used one accelerometer. There's some indication that we may need more than that, either more accelerometers or maybe more sensors within a device. So for example, a gyroscope, it looks like may yield some additional predictive benefit over just an accelerometer for detecting some of these movement types, although we haven't fully investigated that yet.
Yeah, sounds interesting.
This podcast is sponsored by Fibion, a research device that has been shown to be valid in tracking sitting, standing, physical activity and energy expenditure. Furthermore, Fibion has been shown to be valid categorizing physical activity into light, moderate, and vigorous intensity. In addition to scientific accuracy, Fibion provides automatically produced and easy-to-understand reports for research participants. Get scientific validation and learn more about Fibion at fibion.com/research. Fibion, from researchers to researchers.
Do you think you could see something for normal people, like non-athletes, if they, for example, have had an ACL injury? Could you maybe track the progress of the rehabilitation with this kind of application?
There's certainly potential for it. In our analysis that we are currently undertaking, the focus, or at least the setting that we are focused on, is the sport-specific setting. So we're not just putting the accelerometer on someone and asking them to go about their day, but rather we are having them put the accelerometer on right before a practice or right before a game, something that's very purposeful and sport-directed versus just a general physical activity. If somebody's running on the treadmill, you wouldn't expect to see left-right movement, or, on an elliptical, something like that. And so the application of these models is very specific to a sport setting, but it could be done in any population if they're participating in sport, right? So that's kind of the big qualifier, is if they're doing some kind of sport where they are either in practice or in gameplay. Sure, I think these models could have potential application for that type of a setting and population.
And do you think that you could see something in normal daily life, like, for example, just normal walking? Do you think there would be some difference on the sideway movement during walking if you have just came back from the ACL reconstruction surgery?
Mm-hmm. That's a really good question. It's not something we've looked at, but I do think there would be a good research question in there in terms of gait, looking at how symmetric the gait is, or what kind of force is being generated by the affected limb compared to the unaffected limb. I certainly think there'd be something there. The field, at least in terms of objectively or device-based measurement in the ACL or knee injury population, is very, very small right now. When we started our project a few years ago, the only thing that really was available was survey-based questionnaires about general and sport-specific activity. I believe it's called the Tegner scale. I would have to look that up specifically, but they had really no way to objectively quantify those types of movement. The research group I've been working with was one of the first to use accelerometers just to characterize general physical activity in this population, and has shown that in people with ACL reconstruction, their total daily physical activity levels are lower. They take fewer steps. They get less time engaged in moderate to vigorous physical activity. And so but that's all using your standard, like counts from an accelerometer, steps from an accelerometer, and then you use cut points to characterize activity intensity. So those are not methods specific to the ACL population. It's using more of the general accelerometer techniques to understand overall physical activity. And we do know that those individuals were affected for quite a long time. I mean, certainly after the injury, but even after the surgery, out weeks into months, those populations tend to be less active overall. And also, I think it's only about half of people with ACL injury ever return to sport. And so if sport was one of the main modes in which those individuals obtained their physical activity, a large chunk or portion of those individuals are no longer getting that stimulus. And so if they're getting activity, it's likely at a lower intensity. It's probably at a lower total volume following injury. So there are a number of issues, and then that plays out if because most ACL injuries happen in younger individuals, whether that's people in their teens or early to mid 20s, at least within a sports setting. Those individuals, if they alter or lower their physical activity, has large ramifications for health outcomes later in life.
Yeah, I think it could be really interesting just to kind of measure the progression of daily activity. That what is kind of the normal return? When do you return to normal physical activity levels after, for example, ACL surgery? And then you could maybe see that if somebody has some problems, if they don't recover as fast as it should be.
Right. And then you would be able to tag those individuals for special intervention, extra physical therapy. Right. Those are exactly the types of things we're hoping to be able to get at in this type of a population.
Yeah, very interesting. And earlier you mentioned about time sequence, using the time sequences for the analysis. Could you tell more about this one?
Sure. Yeah. So there are some. My research group has worked a lot with machine learning modeling, things like artificial neural networks or support vector machines, decision trees, all of those kind of standard out-of-the-box machine learning models. With those models, again, they all have their own theoretical basis for how they function. For example, decision trees are typically better suited for categorical data, whereas something like a neural network can be used either categorically or for continuous type data. Some have time sequencing, some don't. The big one that I'm aware of that does do time sequencing is the hidden Markov model or the Markov chain approach. And so for activities that have a high time dependency, so for example, I'm sedentary right now, a minute from now, I'm likely to still be sedentary. The minute after that, I'm likely to still be sedentary, right? So activity intensity typically has a strong time dependency. In other words, what you're doing in the previous interval, whatever that length is, will play a significant role in what you're likely to be doing in the next interval. So if I'm sedentary this interval and I'm not sedentary the next interval, it's likely that I'm going to be at light intensity. It would be very unlikely that I'd transition from being sedentary to being vigorous in a single interval, right? So a model that has a time sequencing component can be very helpful in order to understand activity intensity transitions or lack of transitions over time. Within our sport-specific work that we've been doing, we find that certain activities have a very high time dependency as well. So, for example, the lower intensity activities would have a higher dependency. People, if let's say they're walking during soccer or basketball, that is likely to persist from one interval to the next. So they might do it for 15 or 20 seconds at a time. We are looking at activity type by the second. And so you're likely to see multiple intervals then where they would be doing a walking behavior or even a side-to-side movement. They're likely to do for a couple seconds overall, or if they're running on the court, they're likely to be doing that for several seconds at a time. So those all seem to have a pretty high time dependency to them. Whereas other activities, especially instantaneous type movements, jumping or these cutting from side to side, will happen very, very briefly and are unlikely to be preceded or succeeded with another bout of that same thing. And so those activities do not have a strong time dependency to them in terms of what happened in the previous or successive interval. And so what we find is that our time sequencing models, like a hidden Markov model, can dramatically improve our prediction of when people are walking or running or maybe shuffling in a sports setting, but they don't do a lot for us in terms of improving our capacity to predict when people are jumping or when people are doing the side-to-side cutting type movements.
Yeah, interesting, and it makes sense. So how can researchers utilize this? I think not too many physical activity researchers are using machine learning. So how could they use this one?
Yeah, it's a good question. So I think in general, implementation of machine learning models is an issue. It's, over the last, I would say 10 to 15 years, there's been a lot of interest in the field of accelerometry in improving the way we derive meaningful outcomes from our accelerometer data. The first method was, translating accelerometer data into steps or activity counts, and then using fairly simple techniques to change or derive those like activity intensity metrics from counts. Machine learning models are quite a bit more complex, both to develop, but also to the implementation. And so you really don't see on any kind of scale people using advanced analytic approaches for analyzing data. So, your question is a good one. How do we do this without machine learning? I think as a researcher, it's pretty easy to look at your data to get an understanding of if your data seems to have a strong time dependency to it. For example, the way we did it was pretty crude. We would just take a given so we would just look at walking, and we analyzed the number of times, the number of instances in which walking occurred in our data set. But then we looked one epoch or 1 second prior to that and said, okay, if they walked in this interval, what percentage of time did they walk in the previous interval as well? And we got something like 80% of instances where, if you were walking right now, you were walking the 1 second prior to that, even though maybe only 50% of our data set was walking. So the amount of walking preceded by walking was much higher than walking's contribution to the data set. So we were able to have pretty strong evidence that walking was a time-dependent activity, whereas jumping happened, I think, in about 3% of windows in our or of epochs in our data set. And it was virtually never the case that you saw jumping immediately preceded by another interval of jumping. And so that variable we were able to conclude did not have a strong time dependency. And so when we think about trying to identify those things, even if you weren't using machine learning modeling, it might be you might be able to say something about, well, these intervals or these activities with a strong time dependency, maybe they're going to be easier to capture because they're going to happen more together in groupings, right? Whereas the instantaneous type movements like jumping, you're going to have to be a lot more careful about catching. Otherwise, you're going to miss it within whatever you're looking at for your data.
Thanks for joining us this week on Physical Activity Researcher Podcast. If you like the show, make sure you never miss an episode by subscribing or following the show on Twitter. This podcast is made possible by listeners like you. Thank you for your support. If you found value in the show, we would really appreciate a rating on Apple Podcast or whichever app you're using. Or if you would, in a real old school way, simply tell a friend about the show. It would be a great help for us. We have a fantastic lineup of guests for forthcoming episodes, so be sure to tune in. Thank you all for your support and have a great day.